Hello everyone, thank you so much for joining me today. Today we are going to be making a Bohr model. We are using the textbook Exploring Creation with Physical Science, and we are studying Module 13, and there are no experiments in this module. So we are going to be making a Bohr model as part of our learning activities for Module 13. If you take a look in the textbook on page 314 at figure 13.1, the publisher shows, or the author rather, shows a helium atom according to the Bohr model. And so today we're actually going to use some materials you can find around your house to make such a model, but we are not going to do the helium atom. We are going to choose something different. So remember, a model is a representation of something that exists. We do not have the equipment to see an atom in our home laboratory, so we're going to make a model to help us understand it better. The materials you'll need to make your model include a paper plate. A bigger one is better, but a smaller one will work as well. You'll also need 3 different colors of beads of some sort: plastic, wood, whatever you have. You can even take colored straws and cut them into small segments. But you do need 3 different colors and up to 10 of each. You may not use all 10 of each color, but I want you to have them. And then you'll need 2 chenille sticks or pipe cleaners, a marker that will write on the plate. I prefer a Sharpie marker, a pair of scissors, and then, of course, a hot glue gun with glue in it. So how we're going to make this model is one color of beads is going to represent the neutrons, one color of bead is going to represent the protons, and one color of bead is going to represent the electrons. There's nothing special about the colors, they just need to be 3 different ones so you understand which color is representing which part of the atom. Now, over the centuries, different atom models have actually been developed by scientists, and the current most accurate working model that we use now is called the quantum mechanical model, and you're going to learn about that model when you take chemistry. It's a bit beyond the scope of physical science. So in this particular course, you're learning about the Bohr model. And the Bohr model still is quite accurate, and it gives us a great understanding of what's going on in an atom. The problem with it is it's really a 2D representation of particularly how the electrons are traveling, and I'll explain that difference as we make our model. So the first thing that we need to do is decide which atom we are going to be modeling. In the textbook, they show a Bohr model of a helium atom. And I would like you to choose an atom from the periodic table that has an atomic number of between 3 and 10. So let's pull up a periodic table so you know what I mean. Okay, so this is the periodic table that's presented on page 321 of the textbook. And the periodic table, as you will learn over time, provides us tons of information about each of the atoms. And I will tell you that this periodic table is actually out of date. There are other elements that should be on here, as well as some that have been renamed. So I'm going with the one that's in your book, though, just so I don't add any confusion. And the parts that we're using up here near the top of the periodic table are going to be the ones that they're fine. We're not going to run into any information that is incomplete there. So the Bohr model on page 314, figure 13.1, presents the information for this particular element, helium. Okay, now the periodic table gives us a ton of information, as I said, and you're about to learn what that information is. So I'm going to draw this here and kind of blow it up a little bit. What you're actually seeing in that box that is chock full of information. So the first thing that you see is the chemical symbol, and that is He for helium. And these chemical symbols come from Latin, they come from Greek, and they also come from English. Some of the newer discovered ones are named after scientists or places or things like that. Okay, so just So you can kind of keep that straight. So helium. Now above helium's chemical symbol, He, you're going to find a number, and that particular number is known as the atomic number. The atomic number tells us how many protons a particular atom has. Okay, so I'm going to just pop up here. So in our example here, our chemical symbol is He, and this is for the element of helium. And the atomic number, which as I said is this number right up here, tells us the number of protons. Okay, so we can go ahead and fill that in. Helium has 2 protons. Every single atom of helium in the entire universe has 2 protons. Okay, no exceptions there. All right, now, what this also tells you is the number of electrons. Atoms are electrically neutral. And remember, protons have a positive charge. Protons have a positive charge. Electrons have a negative charge. So if we want it to be electrically neutral, that means the same number of protons must exist as the number of electrons. Okay, so if helium has 2 protons, how many electrons does helium have? Hopefully you said 2. Okay, as I said, this is giving us lots of information. Okay, now the next thing that you will see on this periodic table for helium is what is called the atomic mass, and that is 4.0. Okay, now the atomic mass is the average mass of all helium atoms that exist. Okay, you're learning in this module that there is a third component of atoms called neutrons. And although the number of protons and the number of electrons always stay the same for a particular atom, for example 2 for helium, the number of neutrons can actually vary. And those are called isotopes. So there could be isotopes of different atoms or elements as they exist in nature. And that varying number of neutrons is responsible for isotopes and is responsible for the fact that we have to take an average mass of all of the different atoms that exist. So the atomic mass is that average, and that is the number that you're going to find underneath each and every element. No matter what periodic table you look at, some periodic tables might have more information on them than the one presented in your text, but they will all give the atomic number right here on the top of the element symbol, and then the atomic mass right underneath the atomic symbol, or the chemical symbol. Okay, so the atomic mass for helium then is 4.0. Now the mass number, and a lot of these sound alike, which is why I've put it out here for you so you can keep them straight. The mass number is the number of neutrons plus the number of protons. Okay, so we know the number of protons here for helium is 2. So it's something plus 2. Okay, and the number of neutrons, how do we figure that out? Well, it's a little bit beyond what we're doing here, figuring out the isotope numbers. But if we go with the helium isotope, helium-4, and it's either written like this, helium-4, or He with a little 4 up there. If we go with that, then we know that the mass number is 4. Okay? And I'm getting that from here. So if the mass number is 4, and we know that the mass number is the number of neutrons plus the number of protons, then we can solve for n here, and we can determine that the number of neutrons for helium-4 is equal to 2. Okay? So that's rolling all of our isotope discussion into one here. So let's now take a look at the Bohr model. So in the center of the atom, we find the neutrons and the protons. And together they are called the nucleons because they are in the nucleus. So we're going to draw one proton here and a second proton here, and they are stuck tightly together, okay? So I'm using pink for my protons there, and that actually goes along with the color of beads that I'm going to use for the model. Then we have our neutrons. Now neutrons, like the name suggests, are neutral. They have no charge to them, okay? So I'm just going to write this down here so I have a little key. Green is neutron, and the pink is a proton. Now remember from your reading that protons and neutrons, making up the nucleons in the nucleus, they account for the bulk of the mass of a particular atom, and that's why we use it for this mass number and to calculate the atomic mass as well. The electrons, although they are the most important insofar as how atoms interact with one another, they make up a teeny tiny part of the mass of the atom, so we kind of actually ignore it as far as the mass is concerned. And those atoms are circulating in what we call energy levels around the outside of the nucleus. They're way far out. I've heard it described as if we have a sports stadium, like a baseball stadium, and you put the neutrons and protons in the middle of it. Somebody sitting way up in the cheap seats is going to be kind of the distance that the electron is away from the neutrons and protons in the nucleus. And in the Bohr model, we show that the electrons are orbiting around the nucleus. Now, in the Bohr model, it is a 2D representation, two-dimensional representation. And so it makes it seem like, I'm just going to draw that so I can put a negative symbol in there. There we go. Okay, so it seems like they're orbiting like in a flat ring around it. That's really not the case. The quantum mechanical model, as I mentioned, gives us sort of these 3D cloud-like orbitals that they actually travel around in. But this Bohr model will help you to understand at least. And when you take chemistry, you'll learn all about the quantum mechanical model. So because helium has 2 protons, we know that helium also has 2 electrons. And they are in this energy level right here. Okay, and so that is what the Bohr model will look like for helium. Now, when we get to the next element in the periodic table, we actually are going down to what is called the next period. We actually are going to be adding in a 3rd electron, and only 2 electrons can go in this first energy orbital. So we're actually going to have to draw another energy orbital around the outside of it. But I'm not going to draw that here because that is not necessary for helium. Okay, so when you are choosing which element you're going to use for your model, I would like you to choose something between the atomic number of 3 and the atomic number of 10. So something between lithium and neon. You can choose either lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, or neon. Okay, you can choose any one of those. All right, so let's get to our model making here. For my purposes, I'm actually going to choose, let's see, I think I'll choose oxygen. So this is the one that I will be doing. Okay, so again, you can choose any element that you want. I'm going to go ahead and choose oxygen. I'm just going to show you what that looks like on the periodic table here in case you can't see that. So our chemical symbol is O for oxygen. Pretty simple. And put that here and write in oxygen. And the atomic number of oxygen is 8. And remember, the atomic number tells us the number of protons. So we have 8 protons. It also tells us the number of electrons. Remember, these atoms are electrically neutral, so the number of positively charged protons is equal to the number of the negatively charged electrons. Okay, and let's see, our atomic mass is 16.0. Remember, that is an average of all the isotopes that exist, okay? Now, because we're just picking something randomly off the periodic table, I'm going to actually just have you round the atomic mass to the nearest whole number. So, for example, this one is going to be 16, okay? So we're going to say that we're going to use oxygen 16 as our isotope, okay? Now, remember, our mass number is neutrons plus protons, so neutrons plus 8. And our mass number that we are going to use, as I said, is going to be the average of the atomic mass. I should have written 0.0 there because that's how it's presented on this periodic table. So we're going to use the mass number of 16. So that tells us in our particular isotope of oxygen, we are going to have exactly 8 neutrons. Okay, so let's draw out what this Bohr model is going to look like in this space here. How many protons am I going to have? 1, 2, 3, 4, 5, 6, 7, 8. And how many neutrons? Yep, we're going to have 8 of those. And remember, those exist together as nucleons in the nucleus. 2, 3, 4, 5, 6, 7, and 8. Now, the electrons are traveling in orbitals. These are energy orbitals. And according to our Bohr model, a certain number of electrons can exist in certain orbitals. And there's actually a chart that is provided in your book that is explaining that, how many can exist. And that is found on page 324 in table 13.1. So I'm actually just going to tuck that in here for you. So Bohr orbit, and then the electrons capacity. So I'm going to just put number of electrons. So in Bohr orbit 1, 2 electrons can be at that energy level. Remember, each orbit is an energy level. Maximum of 2. If a particular element or an atom has more than 2 electrons, then those additional electrons are going to be at a higher energy level in Bohr orbit 2. And Bohr orbit 2 can accommodate 8. Bohr orbit 3 can accommodate 18. Bohr orbit number 4 can accommodate 32. And Bohr orbit number 5, sorry about that, overwriting there, can accommodate 50, okay? So this tells us how many orbits we're going to need. So back to our atom of oxygen, I'm going to draw orbit number 1 around the nucleus there. And we can put 2 of these 8 electrons here are going to go in that first orbit. So there's going to be 1, 2. Now remember, we have 8 total, so we got to find a place for 6 more. So we're going to draw that as a second orbit here. And how many electrons can that second orbit accommodate? 8 total. Now we only need to put in 6. So we're going to put those in there. 2, 3, 4, 5, and 6. So we have 8 total electrons represented here in our Bohr model for oxygen. So that's what it looks like on paper. And you can go ahead and pause the video here. And I would like you to calculate what you're going to need for your particular element that you are choosing. Calculate, well, first of all, write the chemical symbol like I've done here. and then the element, and then the atomic number, which is the number of protons, then the number of electrons, then the atomic mass. Again, you're getting that from the bottom number here of the periodic table, and then the mass number. You're going to calculate that, neutrons plus protons. So go ahead and pause the video for that, and then we're going to use that information to build the model. Okay, so we're going to take our paper plate on which we're going to build the model, and we're going to put some information about the atom that we are building a model for. So we are doing oxygen. So I'm going to go ahead and write the name of the element there. I'm going to draw what the little box looks like on the periodic table. So you have the chemical symbol of O. We have the atomic number of 8, and we have the mass, atomic mass of 16.0 or 16.0. Then we're going to write the information that we have about oxygen from this. So oxygen has 8 protons, and for electrons, there's 8. And for neutrons, for this particular isotope of oxygen, is going to be 8. Okay? All right, so let's get building. So we need to stick together 8 protons plus neutrons. Now, I think I've actually flipped these colors from my material setup just so it doesn't confuse you, but I was trying to stay consistent. So our protons are going to be pink. Now do be careful because this hot glue gun will burn you. Okay, so we're just going to make a nice little nucleon right in the middle with these protons and neutrons stuck together. And we're going to need 8 of those. 8 of each. Sticky fingers. And by the way, in the module, it teaches you about the strong force. It's the strong force that sticks these together. So you can imagine the hot glue coming out of this hot glue gun is our strong force. Kind of rotate our nucleus around. I'm getting there. So right now I actually have 6 protons in here. So what atom would that be representing right now if it was just 6 protons? If you don't know, look at your periodic table and look for the element that has a atomic number of 6. And if you said carbon, which is represented by the chemical symbol C, then you are correct. But we're building oxygen, so we need to add in 2 more protons. And then here's our last neutron coming in. So here is our nucleus for oxygen. It has 8 protons and 8 neutrons. Together, they are called the nucleons. I'm trying to get the stringy glue away there. Okay, now remember those electrons are orbiting around the nucleus in orbit. So your first pipe cleaner, you want to go ahead and cut it in half because we don't need the entire thing. Okay, and remember how many electrons are orbiting around in that first orbital. for any element other than hydrogen, which only has one, it would be 2. So we're going to string these 2 around. Okay, and then I'm going to go ahead and twist the 2 ends of our first Bohr orbital, and then we can put that around our nucleus. So these electrons would be moving around. Electrons never stay still. So they're always moving around, ready to interact with us. Now remember, this is a 2D model, so it looks like they're orbiting similar to planets around the sun. They really don't. They're zooming around in a 3D electron cloud, which again is represented by the quantum mechanical model, which you'll learn about later. Okay, now we need 6 more electrons. So we are going to bump up to the second energy level, and you're going to use your full length pipe cleaner here. So we're going to put on 6 more. Okay, for a total of 8. And you're going to go ahead and twist those ends together. Okay, and you're going to place that second energy level. And remember, these are zooming around, never still, in a 3D fashion on our 2D model. Okay, so there we go. And lastly, let's go ahead and take our hot glue gun to go ahead and stick these down onto our plate. Otherwise, your dog or baby sister might run off with them and use them for bracelets and whatever else. Okay. And I'm gonna pop those down there. And there you have a Bohr model of oxygen. Well, that concludes our demonstration of making a Bohr model for Physical Science, Module 13. I hope you have enjoyed it and learned something as well. And I recommend that you take a picture of this model and you can put it in your laboratory journal just to show that you did this, although there is no official laboratory write-up for this particular model making experiment. Thanks so much for joining me in the lab today. I hope to see you next time.